Okay, so let's start with what we discussed last week. I will share my screen. Just give me a second. Okay, so let's start with okay. So those of you who have bandwidth problem, they can go to YouTube. You can see on Zoom there is a live on YouTube. From there, you can go to the link, view stream on YouTube, and you can also do copy streaming link. I can post this link in chat window also. This is the link for this session. Okay, let's start. I will go through the lecture number 7 first. Just a quick overview so that you are comfortable. Anybody has any questions, please feel free to ask in the chat window, or you can unmute yourself and ask questions. So I'm opening now lecture number 7. Okay, let me share my screen as well. Okay, so you can see lecture number. So we discussed about signal representation. Tensors are simply a scalar is a zeroth order tensor, and if you have let's talk in terms of programs. If you have a program, what do you say, a Python program, then when you write x I, the only single index, then that is a one first order tensor. It's simply a vector, right? As you have seen in your discrete time signal, you have hn. N is a single index. It can take any number of values. N can take, let's say here it is taking 0 to 3, means 4 values. But since there is only a single index, so you call it as a first order tensor. Second order tensor will have two indices like x, m, comma n. It's a matrix. Then third order tensor will have three indices and so on. And the third order tensor will have n indices. Now the thing is, how do we measure differences between two different vectors or two different matrices or any two different objects, mathematical objects? How do you find the distance? Why do we need to find the distance? Because, for example, when I say, uh, if I show you an object and I ask you, is it a chair? What will you do? You have some representation of chair within your own understanding, and you will compare it with that understanding. Okay, does it look like a chair or does it look like a table or like that? You will do a comparison. So you need a distance measure, that is it closer to a chair or closer to a table, right? So that's how you uh, can think of classification or recognition as a space in which there are distances. So let's say in the so we're going to look at some of the basic distance metrics. Like Euclidean distance is very familiar to all of you. You can know this is a vector, this is a vector. What is the Euclidean distance between the two? Just subtract the two and square all their elements and sum them over and take the under root. That is a Euclidean distance. And then you can have other kinds of metrics also, like you can have Oops, what is happening? You can have a cosine similarity matrix where you can have uh, two vectors. They need to be normalized, length normalized. So these they are unit length. So x1 upon norm of x1, x2 upon norm of x. This could be the L2 norm. L2 norm means simply the Euclidean norm or the Euclidean length. And you take the dot product between these two vectors. That is the cosine similarity matrix. So the closer, so okay, compare cosine similarity with Euclidean distance. In Euclidean distance, the more the distance, the farther are the points. But in cosine similarity, the more the cosine similarity, the closer are the points, right? Because cos 0 degree is 1 and cos 180 degree, when they are exactly opposite, that is -1. So cosine similarity, that is why it's called similarity. More the similarity, the closer they are. And why we call it a hypersphere? Hypersphere means it's a sphere, which means a unit length vector, but it could be in any number of dimensions. So if it were only 2 dimensions, it were a circle. 3 dimensions, sphere, but any number of dimensions, in general, they are called hypersphere. So, sorry, how do we measure difference between two probability distributions? Now we saw two vectors. How are the two vectors different? But now let us say it is not. These are probability distributions, which means essentially vectors, but they are all non-negative and they sum up to 1. Right? That is the meaning of probability distribution. These are vectors, but they are non-negative and they sum to 1. So you know KL divergence is a measure which can be used. I'm sure you all know what is KL divergence. Basically, it is P1 log P2 upon P1 summed over all the what do you call it? All the sample space and with a negative sign. Okay, what happens when P1 approaches 0? When P1 approaches 0, then this P1 is also 0. So although log of something very large will become very large, but this is also 0, so that does not count. Okay. Of course, here if P2 becomes 0, that will become problematic, right? When P1 is non-zero but P2 becomes 0, that becomes problematic. Okay. Now these are some real examples. Okay, so you have two vectors, but you can find any kind of distance between the two. It could be what to say, Euclidean distance, or it could be cosine similarity. But does that make sense? These are mathematical operations and we are working in real world. Does it really make sense? So the answer is no, it does not make sense in general for everything. So an example is given here. These two signals, if I'm comparing how they sound, these are sound signals, audio signals, if I play them, they will sound exactly the same, right? But if you see, this is a positive peak, this is a negative peak. This is a negative peak, this is a positive peak. So if you take the cosine similarity, that will be very small. If you take the Euclidean distance, that will be very large. So, but if you listen to these two sounds, they are exactly same. This means this auditory perceptual distance is not cosine similarity or Euclidean distance. So you have to find some other metric which captures this perceptual similarity. So what I mean to say is that the mathematical representation may not correspond to perceptual representation. So that is the whole point of machine learning. How do we learn perceptual metrics or perceptual distance or perceptual similarity, and not just work with mathematical similarity? Signal processing earlier was designed to do it, but machine learning these days is trying to make it much better. Okay. Another example is from the vision domain. These two are exactly same numbers, right? This is 2, this is also 2. But if you find out the, let's say these are two matrices, if you try to find out the Euclidean distance between these two matrices, that distance will be very large, right? Because element-wise difference will be very large. That's why Euclidean distance is very large. But you know that for my visual perception, these two are exactly same digits, 2. Okay. Uh, so which means I have to do something. Okay, it gets more complicated. If you have some person, then that person, if you look at, this is the same person, right? But still, uh, the the pixel wise representation or the matrix representation will be so different, will be so different. So how do we do this perceptual mapping, understand the perceptual space? uh, Now the thing is that I will introduce one more concept. Okay, so depending on what I am perceiving, my space may change. For example, if I ask you who is this person, the answer will be same. All three are same persons. But if I ask you a different question, okay, what color jacket is he wearing? Then this case black, looks like black or maybe bluish. This case orange. So these two are same, but these are different. I ask, what color turban is he wearing? Then same in all three cases. Then is he holding the stick in the right hand or left hand? Right hand, right hand, right hand. So okay, right hand. Or this. What color shoes he's wearing? Different. This is purple, blue, and this is maybe pinkish, something like that. Blue, black, pink. Okay. So different. So means what I mean to say is that, depending on what question you're asking, the distance metric or the space may change, right? So different concepts are um, represented differently. Okay. Now, what is lacking in our mathematical representation? Answer is the space. As I just told you, the perceptual space is different from mathematical space. So for example, the food that we eat, apple versus banana, I give you one apple which is green in color, one apple which is red in color, it will taste the same. But if I give you a banana which is yellow in color, it will taste very different. So um, similarly, I can give you one apple, the shape is round, an orange, the shape is round. In the shape space, they are same, but if you eat, they are very different. Sounds you listen to. Similarly, you can find so many examples that I can play saregama with a violin, or I can play saregama with a flute, I can play saregama, I can sing it. All are same notes, same music, but the source is different, right? So the space is important. How do we represent? So okay, so perceptually, I can see that what things are similar, what in what uh, on what dimensions they are similar, or means on um, um, what factors are similar, or what aspects are similar, what aspects are different. But how do machines do it? That is the question which will be answered, which we will try to answer in this question, or some popular techniques which try to do it, so which allow machines to do it efficiently. Okay, sensors or detectors, they correlate with what we experience. So basically, I'm experiencing these two are same digits, but or I'm experiencing these two are same sounds, but what detectors or sensors are needed to capture that sound and put it into mathematical representation, then what algorithms are required to, or what space is required to represent those sounds so that mathematically also they correspond to my perceptual space, right? Means similar sounds are together and dissimilar sounds are far apart. And this is the punchline. Similar objects are together, dissimilar objects are far apart. That is the meaning of space. So space gives identity to every object, and it gives existence to every object. That is the space. So where is the sound? Sound is in the space. Okay. Okay. What are detectors? I think these things you can read. These are very easy. Feature extraction. Yes. So this is the typical signal processing based approaches. So in signal processing based approaches, we try to extract features which are like what we are interested in. For example, if in music I'm interested in notes, then I will extract features like pitch, etc., which correspond to that aspect of my perception, and then I will be processing these features, or I will be playing around with these features. Let's say I'm interested in music, I'm interested in notes, or the frequencies, then I will extract these notes and I will play around. Okay, this song is playing sarega, but this song is playing Mapadha. And then this means these two are different sounds, different songs. Same songs will have same notes, things like that. So I can process at that level then. I don't process my original raw audio file, but I extract these useful quantities and I play around with them, or I process them. So, okay. So that is the philosophy of feature extraction. It was very popular with the signal processing approaches, but nowadays, how do machines do it using machine learning approaches? That is what we are doing. Okay. Now, audio. Okay. I think these things you can read, how we record audio, different things about audio, that what are the, what is frequency, what is sampling, what is quantization, and how do we represent audio? It's a stream of numbers. What is pitch? Pitch means the uh, like different musical notes, they have different pitch, and they are like as you have read in previous lessons about f naught, the fundamental frequency, basically the repeating pattern. What is the fundamental repeating pattern? That gives you the f naught, right? Loudness. So basically these are how different perceptual attributes they correlate with the mathematical attributes. That is what we are doing here. Okay. And audio representations, I think. And then in images, you have these. I think I can, yeah. These are some references. You need not go through all of these, but in case you are interested in more details, then you can do it. Okay. Anybody has any questions in this part? So basically what we said is we have a perceptual space and we have some mathematical numbers, mathematical representations. How do we make our mathematical representation represent my perceptual space? So we discuss different techniques in this lecture. Anybody has any questions at this moment? Please feel free to ask until I change my slides. I will go to the next lecture slides. Lecture 8. Okay. No questions? Am I audible?
Yes, sir.
Okay, thank you. I thought I'm not audible. Maybe that's why people are not asking questions. Okay, let's share. I will share my screen now. Lecture number 8. Okay. Okay, so this is machine learning now. Okay, we saw how do we represent our uh, uh, different kinds of signals, like audio signals and images. So how do we represent them? Okay, now we want to process them. We have represented them. That is our input. Now we want to make a model which will transform this mathematical representation into a space which corresponds to, or which is closer to, our perceptual space. Let's say, I'll give you an example. I show you an image of 2. You remember the image of 2? That is my input. My output will be, let's say, some representation. Let's say the number 2. And then if I pass the other image, which is the shifted version of 2, then output will be the same. It won't be different. But if I pass here 1, the output will be different. So like that. If I have passed here one picture of some person and another picture of some person, both will map to same output. But if I pass here a picture of one person and picture of second person, they will map to different outputs. That is the thing. So this is the basic idea of machine learning. You have some input to a model. This model will give some output. that output is very is more meaningful for, from perceptual point of view. An example could be classification. I want to classify flowers. This is a rose, a lotus, and a jasmine. I want to, given an image, I want to classify whether it's a rose or a lotus or a jasmine, right? So my answer will be one of these three. Either it's a rose or a lotus or a jasmine. And my input is, let us say, these images. But now these images are very high dimensional and a lot of processing is required. So I can represent this into a lower dimensional thing. Let's say I just extract my height of the flower and the diameter or the width of the flower, x1 and x2. And I just use this information to uh, to as the input to my model is the height of the flower and diameter of the flower. I'm not giving the color, I'm not giving the image, nothing, just the height and the diameter. So two uh, uh, just two a vector of length 2 basically. Just a vector of length 2 is my input, and my output is one of these three flowers: rose, jasmine, or lotus. Now this is one example. You can see I have, so when I want to train my model, so that my model behaves the way I want it to behave, I need some training data. What is training data? It means some pairs. You have X as well as Y. Your X is the input, Y is the desired output, the target output. And so this, my X is here. Let's say these are the roses. These are the blue ones are the, let's say, lotuses. So rose versus lotus. And I'm given a new flower. This is my test case. This is a test sample. I don't know the label for this. Now my machine has to automatically label it. Let us suppose I am the machine. So what will you label it as? You may say this is a rose, or you may, if I give a point here, let's say here, what will the answer be? Maybe I think you can all answer. You can write on the chat window. I expect your responses on the chat window now. If a point is here, a black dot appears here, what is this? Yes, this is a rose. Thank you. Thank you. I think everybody is giving the right answer. It will be rose because it is very close to other rose samples. It looks like this space is divided into two areas. This part is rose, this part is lotus, and everything what appears here must be a rose. This is our assumption, but it works. Okay, our assumption is that this space is well uh, well behaved, right? It is not. It won't happen suddenly one lotus appears here, or suddenly many lotuses appear here, right? There can be one or two lotuses which are odd man out, like which are very rare kind of lotus. For example, sometimes you find two bananas joined together, right? They are very rare, but they do exist. Similarly, you may get a lotus which has got which exists somewhere here, but that lotus will be a kind of very rare entity, not a very frequent one. We are more interested in more frequent entities. Okay, so now you will say, yes, let me divide, let me decide a, let me design a classifier which is like this. It's basically a line, and this line has got an equation y equal to y equal to mx plus c. So I can say x2 minus mx1 minus c is equal to 0 on the line, and above this line it's greater than 0, below this line it's less than 0. And if it is greater than 0, I say it is a rose class. If it is less than 0, I call it a lotus class. But now my unknown point lies above the line, so I will say it's a rose class. But I know it is a rose class, hard classification. But a better answer will be, yes, it is a rose, but with the probability of only 60%. And there is 40% chance it could be lotus as well. Why? Because this point is very close to the line, right? That is why it is a 50-50 chance, or means slightly more chance that it is a rose, but less chance that it is a lotus. But still, I'm not very sure. For example, if the point would have been here, I would have been very sure that it's a rose. But since it is somewhere close to the boundary, I'm a little less sure that it's a rose. So this is called soft classification. It means that I am also showing my confidence in my answer. So here I have a low confidence, right? I have a low confidence, but if point would have been here, I would have said probability that this black dot is a rose. This is, let's say, 0.99, which means very high confidence. Okay, well, that is so how do I achieve this soft classification? I can use here a sigmoid function, which is of this form. It's a very popular function, and you will be seeing it a lot more in the coming lectures, especially in the neural networks. A sigmoid function is very popular. So I think you take note of this. Okay, so Diksha is asking one question. What's deciding the probability value here, or is it just an example? The answer is yeah, it's just an example. It's just I have just picked a number. It's an example. Okay, now what to do with this scenario where you have a lot of intermingling? Means the space is not dividing these two classes very nicely, but still there is a lot of interspersing involved. So let's say you have a point here, you have a line here. What will you do? If you, okay, so in this example, what is the accuracy? You have got two blue points wrongly classified and two red points wrongly classified, right? Two lotuses are misclassified as rose and two roses are misclassified as lotus. So what will you do? What will you do in this scenario? So uh, anybody will say, like if you ask me, is this a good classifier? I will say, yes, this is a good classifier because it's doing equal mistake in both the sides. But this may not be always a good strategy to put my classifier, because I know that there are certain cases where the red mistakes harm more than the blue mistakes. Means if you misclassify a red point, that may harm more. For example, let's say it's a fraud detection. So you go and insert your credit card, and the machine reads the card. It has an automatic, let us say it is an automatic machine learning classifier which classifies whether it's a genuine card or a fraud card. So if the machine finds if the machine fails to catch a fraud card and it dispenses the money, then you are at a big loss, right? You lost all your money. But on the other hand, if you are inserting if the machine uh, um, yeah, let's say if you inserted a genuine card and the machine said no, it is a fraud card, and machine refuses to dispense money, what will happen at most? Okay, you will go to the bank and you will withdraw the money from the bank, or maybe you can try again, right? There are so many options, so you won't lose anything. So which means a genuine transaction being misclassified as a fraud transaction does not harm as much as the other case. Which means if a fraud transaction is classified as a genuine transaction and the money is dispensed, then it will be a big case. It will be a big um, um, loss. So that is the point which I want to make here, that uh, always it is not true that equal mistakes on both the classes is a good strategy. Sometimes, depending on the application, you may want to have more uh, confidence or more caution for detecting one class. Okay, now the question from Vibhor Kumar is, why are you assuming that the boundary is a straight line? Okay, I am using linear models. Yes, so this is my model. My model is a linear model. That's why it's a straight line. If I use nonlinear models, it will be a not straight line. It's a nonlinear boundary. Uh, but the concept remains same. The concept is that certain kinds of mistakes harm more than other kinds of mistakes. Okay, so here comes the answer to your question before. We can have curves also like this. We can have like this is a piecewise linear classifier. Okay, so so basically to get this is a nonlinear classifier, and we can use neural networks, which are nonlinear classifiers to achieve this kind of a classification. Now, the basic philosophy of machine learning, you have training set and you have test set. Training set will have, as I told you, you have inputs, and you have targets, and you want to use this information, the paired information, that for this sample x1 the target is y1, for this sample x2 target is y2. This is the image of a rose, this is the target, the label rose, image of a lotus, label lotus, like that. And but in the test set you have only the inputs. I just give you an image of rose, or I just give you the height and width of the rose. I don't tell you what target it is. Your machine has to tell the answer. So it is like in an exam, or when you have your exercises in your textbook, there will be questions and answers. So this is X is a question, Y is the answer, right? You read the questions, you read the answers, and you learn from there. And then finally, in the exam time, the test time, you will have only questions, and answers you have to tell. You have to guess the answers. And then the teacher will compare your answer with the correct answer, the unseen target, means unseen by you or unseen by the machine. And the teacher will compare your estimated answer with the uh, actual, it's called ground truth, the actual answer. And if the comparison, if they match, you say yes, very good, you get marks. If they don't match, then you don't get any marks, or you may get negative marks also in some cases. Okay, so that's the philosophy of machine learning. There is a good reference here. Christopher Bishop book I have already shared with you as a reference. It's available online. It's a free of cost open source book by Christopher Bishop. Chapter 1 is very good. It's very well written and it explains the concepts very nicely. I would highly recommend that you read this book, especially chapter 1. Chapter 1 is, the title is Introduction, but it is a very detailed, very thorough introduction. Okay, thank you. Anybody has any questions? So we are done with this chapter. Next chapter I will start now. Sorry, it means next lecture, lecture 9. Just share my screen. No questions? Okay, so let's start with the next lecture. Okay, so machine learning introduction. This part you have already seen. Now, evaluation measures for classification. When you're classifying two different classes, or when you're classifying a sample into one of those classes, it could be, so how do you compare, as I told you that in the exam, you give an answer and the teacher will compare your answer with the correct answer. If they match, it is you get points. If they don't match, you may get no points or negative points, or you may get less points, right? So uh, let's say this is a classification problem, which means you can have let's say this in this example. So let's say I'm detecting roses. In this case, let's say my problem is to detect roses. So how will I evaluate? So to evaluate, I can say actual. Actually, it was not a rose, and your algorithm also predicted it is not a rose, right? Then you can add things up here. Or it could be actually it was a rose and your model also predicted it was a rose. So you can add things here, right? You see, let's say out of these, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Out of these 10 samples, 10 roses and 10 lotuses, I'm detecting roses. So my positive class is the rose class. Let's say my actual is rose and my predicted also is rose. So how many such samples are there? Actual is rose. I think I will keep this more interactive because this will be a good exercise for you, because there are some questions. Let me answer these questions first before you write answers. The first question is how those probabilities are calculated in soft decision boundary. Okay, so as I told you, one way to do it is using sigmoid function. If I use sigmoid function, I can convert my numbers into a probability distribution. Okay. If there is a lot of cluster near the partition line, can we say space is not right for the evaluation? Yeah, if there's a lot of cluster near the partition line, then we have to do something to make the space better, that the space separates the two classes better. So we have to do some more engineering to make our things work better. And okay, yes, you've said, can we say that space is not right for the evaluation? No, for evaluation, it does not matter, but for classification, it is not right, right? Evaluation is just a procedure where you assign the, okay, what is the accuracy of this model? That is all right, but accuracy is low, that is the problem. Okay, okay, let us come back to our question now here. Okay, I think everybody's questions are answered. Okay, now my question. My question is, what will be the number here? Actual is a rows, predicted also rows. How many such cases are there? People are saying 8. Yes, answer is correct. 8. How 8? Okay, actually they are rows. So whatever here are the rows. Predicted should also be rows. What are predicted as rows? Whatever is above the line is predicted as rows. So how many of these are above the line? 8 are above the line. Yes, so answer is 8 here. Now come here. Actually it is a rows, but predicted as not a rows. How many such cases are there? 2. Yes, very nice, very good. So which means the actual rows is which are below the boundary, because below the boundary means the machine is saying it's a lotus. So machine is predicting it as a lotus. So these two red points are, so there are 2 points, I will say 2 here. Now similarly you can do here, it will also be negative, negative means it's a not a rows, and classified also as not a rows. So how many such cases are there? 8. Yes, very good. So 8 blue points which are below the line, they will come here. And similarly, what will come here? Actually, they are not rows, but detected as rows. 2. Yes, very good. So 2 points. These 2 are the points. Okay, I think you got it very well. Now there could be, this was an example with only 2 classes. I can have multiple classes. Let's say I can have rose, lotus, jasmine, rose, lotus, jasmine. So accordingly my matrix will become larger. So the size of the matrix will be 3 cross 3 because there are 3 classes. So if there are n number of classes, then the size of my confusion matrix will be n cross n, right? Okay, so this is the thing. Let's go to another metric. Okay, so this confusion matrix is a very detailed metric. It's a very nice metric to do error analysis. What kind of errors my machine is making? For example, you can see here, looking at this matrix, you can say rose, lotus, jasmine. So what is the class with which roses confuse the most? Rose gets confused with a jasmine 20 times, with a lotus 60 times. I think this is a very confusing combination. So it means roses getting confused with lotuses. It's large number, right? So this confusion matrix gives you how much confusion do they have, right? Now another metric which is a 1 number metric. See, confusion matrix was n cross n values were there. But if you want a single value to compare two different algorithms, then we need something else. So let us say accuracy is one such measure. There's a question from Diksha. What's that GT predicted table below X1, X2 graph? Okay. Okay. Yes. So what is this table? So let's say for this sample, for this sample, the ground truth is a rose and predicted also is a rose. So this sample is represented by this. As a row, ground truth is a rose, predicted also is a rose. Let's say there are only 3 samples. Second sample, it's a rose, but predicted as a jasmine. Third sample, actually it is a lotus, predicted as a rose. This is a hypothetical example. It is not correlated with this image, but just to show that this is how generally you get the outputs. You get your model will give some predictions. Sample one model will say sample one is a rose, sample two is a jasmine, sample three is a rose. But your ground truth, sample one was a rose, sample two was a rose, sample three was a lotus, right? And then you compare these two, or you from here you can construct a confusion matrix and find out these good metrics. Like accuracy is one such metric. Accuracy means number of correct hits divided by all the samples. So number of samples which are correctly classified divided by number of all the samples. So, okay. Okay, so if you look at the matrix representation, what will be the accuracy? Let's say if I give you this, what is the accuracy? So this is the correct, this is the correct. So this plus this divided by the sum of all the entries. So this entry plus this entry, these are the correct ones, right? The diagonal elements are the correct ones. So divided by everything.
Yeah.
It will be 80%.
Huh? Oh, ठीक है.
Okay, so yeah. So accuracy is basically trace divided by sum of all the elements. Trace means the sum of diagonal elements divided by sum of all the elements. That is the accuracy. Now, it is very much possible that accuracy is not a good measure. When will that happen? I think you have seen in the video also. I've just quickly explained. So let us say you have very large. So let's say this problem is detecting corona, detecting corona. So very few people will have corona. Most people will not have corona. It's a rapid test, let us say. So now in the rapid test, if mostly people don't have corona, let us say this is the example. If mostly people don't have corona and my rapid test is a fake test, it always says no corona, no corona, no corona. So all these 10 people who actually had corona, they're also put into the same basket that they don't have corona. So this test is basically a fake test, let us say. But still, if you compute the accuracy, what would be the accuracy? So trace divided by everything. So 0.99, 99% accuracy. But if you look at another test, which is more genuine, let's say the rapid test, this is more genuine, but it does so many mistakes. So 960 people didn't have corona, and he said, yes, they have corona. 10 people had corona. It's 5 people, they said they have corona, 5 they don't have corona. Accuracy, trace divided by everything, so 9.65%. So accuracy is low, but still this classifier is better than this classifier, right? This is just a cheating classifier. There is no classification here. It's just a cheater. But this one is at least doing something. So this classifier is certainly better than this classifier. That is why accuracy will not tell you that. Accuracy is not a good metric. So what do you use there? You will use precision and recall, the other metrics. What is precision? Okay, I will tell you one example here. Let's say it's a detection problem, and you have to raise your hand. Whenever, let's say, corona test or any detection, corona test, let us say, so you are a classifier. Whenever the sample is a corona positive, you have to raise your hand. Whenever you think it's a corona positive, you raise your hand. Whenever you think it's not corona positive, you don't raise your hand, right? And so precision is true positive divided by true positive plus false negative. Look at this graph here. So what are true positives? So when ground truth is also positive, prediction is also positive. So that is true positive. So when person actually had corona and you also raised your hand. So which means, and divided by true positive plus false positive. False positive means person did not have corona, but you raised your hand, right? So precision means the fraction, how many times you raised your hand correctly. So you raised your hand 10 times in this case, out of which 8 times was correct and 2 times was incorrect. So what is the precision? 8 divided by 10. You raised your hand 10 times, but out of which only 8 times you raised correctly. So it is raising your hand. Precision is like raising your hand correctly divided by total number of hand raises. On the other hand, recall is now you won't count number of hand raise. You will count the number of people who actually had corona, who were detected as corona. True positive means you raised your hand when the person actually had corona, and so this is true positive. What is false negative? False negative means person had corona, but you did not raise your hand, so he was not caught. He was taken as a negative, but actually he was positive. The false. So recall. This is recall. So basically, in other words, in one line, if I have to say, so number of people who actually had corona and who were correctly detected divided by total number of people who had corona. So means, in other words, uh, detected positive cases divided by all the positive cases. Means, I mean, when I say positive, means the ground truth is positive. So uh, like people who were detected to have corona correctly divide by all the people who had corona. Actually, that is recall. And then recall and precision are two different measures, but they can be combined to form a single measure. It's called F score, which is basically the harmonic mean of precision and recall. There is a question from Ratnesh. For the best model, what matters most? Yes, very good question. So a good model should have very good accuracy. And if it is a detection problem, then a good model should have very good precision and very good recall and very good F measure. Means good means large values. It should have high accuracy, high precision, high recall, high F measure. Everything should be high for a good model. And which is more important, that depends from problem to problem, right? Whether you want more, let us say you cannot make a model which gives you 100% precision, 100% recall, which means you have to do some balancing, that if, because my precision may go up, my recall may go down. If my recall goes up, my precision may go down. So if I have to find the balance, then how do you find the balance? That depends from problem to problem. So, okay. So these two things can vary. This is the plot, typically how it happens. If I change my operating point, or if I change my threshold, what is the threshold? Let's say this is the line. Line is mx plus c. What is m and what is c? Okay, tell me if this is a line, mx plus c. Tell me what is roughly the value of m here in this line. Just visually, quickly tell me. This is a line, a linear classifier, y equal to mx plus c. What is m here approximately? 45, 45, 1, 1, 1, 1, 1. Okay, 1, yes. So yeah, those who said 45, it will be tan 45 degrees, right? Tangent 45 degrees, which is 1, right? So m is the slope. Slope means tan theta. If you say this is the theta, then tan theta is the slope. So yeah, it is 1. And what is the intercept? C, roughly 2, minus 1, minus 1, minus 1, minus 2. Okay, yeah, so correct. So we will have basically a negative number. So my C is basically the y-intercept. So where does this line meet my y-axis? It will meet somewhere here. It could be some negative number. I don't know what exactly, minus 1 or minus 2, depending on your scale, because there are no numbers here. So it's some negative number, minus 1, minus 2 or something. That is my intercept. Now, if I change my intercept, my line may go up and down, right? If you remember this fraudulent case, if I move my line down, so here my fraud detection, my recall is perfect. My precision is not very good, but recall is 100%. And if I move my line up, that all the blue points are below the line, then my precision will be very high, but recall will be not good, right? So based on my C, I can choose my precision versus recall, right? I don't have to change my M. Let my M be same. Just by changing my C, I can change precision and recall. And this is true when you have very big models where the, let's say it's not just two-dimensional, it is multi-dimensional. then I can't change all the slopes, all the weights, but only one single threshold which I change, which is basically it moves the lines up or down, or if it's a plane, it moves the plane up or down, or if it's a hyperplane, it moves the hyperplane up or down. So only one threshold I change basically to decide my operating point. Operating point means uh, how much precision and recall I want finally. If I operate here, my recall will be 1, precision will be almost 0. If I operate here, precision will be almost 1, recall will be almost 0. So I don't want that. But what I want is I want a good uh, trade-off, depending on my application, of course. Okay, this is a good problem. Give some practical examples where you need high precision, but by compromising recall, and give some examples where you need high recall but low precision. I gave one example of corona detection. Oh, fraud detection, just like just now we discussed. Which case is that? Fraud detection. Fraud detection. Yes, I need high recall. I need high recall. I don't want to miss any fraudulent case. If I miss a fraudulent case, I will lose all the money. So I need high recall, but precision can be somewhat compromised. And what will be the other example? I need high precision, but recall can be somewhat compromised. YouTube recommendations. I need high precision. Oh. See, these are detection problems. Detection problems. YouTube recommendation, can it be framed as a detection problem? I don't know. Email spam detection. Okay. Yeah, that's a good example. Email spam detection. Yes. I need high precision. If something is classified as spam, it must be a spam, because if it is not a spam, then you may lose some important email, right? I think email spam detection is a good example of high precision but compromised recall. Okay. Then there are some typical steps. I think you have heard this in the lecture. I will just not read it because I have only 5 minutes left. I will discuss the assignment with you. Pattern recognition and machine learning. Yeah, same book, section 1, basically chapter 1, section 1, chapter 1, section 1. Okay. Okay. Now, anybody has any questions, please write on the chat window. Otherwise, I will share the screen to discuss the assignment. Means just the questions, not the answers. Please ask questions if you have. Mm. Please ask questions. I am opening my Jupyter notebook so that I can discuss with you the assignment. Anybody wants to give any feedback or any? Anybody has any questions in the assignment? The deadline for assignment submission is Saturday night, uh, night 10 o'clock. So I hope some of you, I hope you have all started working on it. It's not very difficult assignment. It's very easy assignment. It's the first assignment. So uh, you may need some help. So please ask questions. How to open file in Jupyter Notebook? Okay. Okay. Anshul has a question. How do we know our functions are correct? Okay. Let me share my screen first. Okay. So you can see this. How to open it? If you don't have Jupyter installed in your machine, you can use Google Colab. Use Google Colab or Microsoft Azure. Anything you want to use, you can use. And if you go to Google Colab, you don't need anything. Just open this file in Google Colab and start working on it. Everything is ready. But if you want to install Jupyter on your machine, I'm using Anaconda. Basically, I'm using my system. You install Anaconda, and then I think it's very straightforward in Linux-based machines. But Windows machines I have not used, so I'm not sure. But you can find good tutorials on the internet telling you how to use Anaconda in Windows. Okay, so this is okay. So let's say these are the libraries which I'm importing, and if you're able to import these libraries, very good. These are some functions which you need for plotting. You don't have to do anything here. Let it be like this. So basically, it's matplotlib library, and which I'm using. Plot discrete means it plots like this. So it's a stem plot. Basically, every discrete value 0, 1, 2, 3 will have a point, will have a value, and that value is represented by this dot, and this height is basically this is the representation for discrete signal. It's called a stem plot. This is just Python terminology. Then continuous values, I don't think we are using this function in this assignment. And then generate sawtooth signal. This is how it looks like. So X generates sawtooth this. I have given this solution. Okay, so the question somebody asked on the chat window, how do we know if our functions are correct? So we have given these plots to help you understand that if your answer is correct or not. If you do this, if you run this command and you get something similar plot, then you can be roughly sure, okay, maybe your thing is correct, right?
Sir, yes, right. Sir, one question. Hello?
T should be 4 instead of 0.4. So this T is in seconds. If you see the question, capital T is time period in seconds. And sampling rate Fs is in hertz. Okay, please note it down. This sampling rate Fs is in hertz. So T is time period in seconds. This is important. The units are important. Here also it should have been hertz. Please note down, it should be hertz. Sampling rate Fs in hertz. So T is 0.4 seconds. How many samples it corresponds to, that you can compute. Okay. Now downsampling means okay. Pooja is asking the question, can we import signal from SciPy to plot sawtooth? Plotting is already done for you. Just use that module to do the plotting. But anyways, plotting is just to help you visualize things. But these functions don't need plotting. The function which you have to write your code here. This function will need only, you have to write the code here. And this just needs to return the correct output, X.
Sir, yes, right, sir. Hello? Yes, sir, one question. Sir, you said that we have to use your plots as reference. So will the evaluation be done will the evaluation will be done by seeing the plot only, or are you going to look for the codes as well?
No, for evaluation, we may not look at your plots. We need the correct outputs from the function. And the test cases may be different. Like this is one test case which I have given. It may not be the same. It may be different test case. These values may change for testing. Can we use, there was a question from Pooja, can we Can we import signal from SciPy to plot sawtooth? Oh, plotting is not an issue. You just have to return the correct vector X here. Can we use NumPy functions for sampling from normal distributions? Yes, you can do. You can use NumPy functions for sampling from Gaussian or normal distribution. For example, to do the first question, I first made single sawtooth and repeated. Yeah, because if it is not an integer, what will you do? So yes, maximum amplitude of the sawtooth is shown around 0.8. Oh, really? Okay, my mistake. Sorry. Yeah, it should be between 0 to 1. Okay, this may be a point. Yeah, you're right. This plot has a problem. It should be between 0 to 1. Okay, got it. So you're right. This should be between 0 to 1. Maximum amplitude should be 0, should be 1. Yes. Well, correct, but inefficient program without it full marks. Correct, but inefficient. Yes, in the beginning, because many of you are learning Python, it's all right. The output should be correct. Okay, I think we can stop here. Okay, let me just see if downsampling. I think all these things are very self-evident. If you have any questions, please ask on the, what do you say, in the forum, so that everybody gets to know the answer. Like today we found one thing that FS should be in hertz, the units should be in hertz, which is not mentioned here, but somebody can post on the forum so that everybody knows it. Why do we divide by this to convert int16 to float? Okay, int16 varies from minus this number to plus this number. So to curtail that range from 32767 to -1 to +1, we convert it into float. Amplitude is correct. It would be actually this for this Saksham, for this, why do we divide by this number to convert int16 to float? If you just do a Google search how to convert int16 into float, it will tell you how to do it, right? Actually, I should not have written it there, but since you are very new, so I wrote it there. Basically, just do a Google search. How do I convert int16 to float, especially for audio thing? Then you will get to know it. Amplitude is correct. It would be near to 1 at the end of the cycle, where it will be. Okay, Anshul is saying amplitude is correct. Okay. Okay. Yeah, I think, yeah, Anshul, you are correct that I don't remember how I wrote this function, but yes. Amplitude is correct in the plot. Okay, fine. Can we use any other library for the task here? It is mentioned in the top of this assignment that no, you cannot use. Use only NumPy library for computing and signal processing. No other package is allowed. But we have used here scipy.io. That is all right. So this function we have provided to you. So you can use this scipy.io wave file. This you can use. Okay. So thank you very much. We are 5 minutes past 3. So we can stop here. Any more questions, please post on the forum, right? Forum is there for you. Please post. And also, if you post there, you can ask the TAs also. And let me know if you need any more help, because this is for the first time we are doing it online. I don't know if you need any more help. Let's say you want to have a session with the TA or have a doubt clearing session, do let me know. And this assignment deadline is on Saturday evening, and most probably by Saturday I will release another assignment so that which you can submit, which you can do in the next week. And then soon we will have quizzes and we will have programming quizzes. So, but don't worry, they will be simple. Okay, thank you very much. See you soon. Bye.